So now I'll start the talk. Okay, so this is joint work with Menachem Megador and Martin Zeeman. It really, for us at least, is a nostalgic trip across the early days of set theory and large cardinals. So think of this as a remix of classic 60s and 70s rock and roll, but using modern technology. So here are the elements of the talk. First of all, cardinals with compactness properties. So this is the origin of large cardinals. And in fact, we're going to be going back to 1962 and 1963. We'll be using techniques for proving determinacy. And particularly, we're going to be putting together strategies from 4 different auxiliary games. And these games will have transfinite length. The point of this is something about precipitous ideals, or strong ideals, so precipitous ideals and saturated ideals, and a collection of ideals that I think of as Laver ideals, because Rich Laver showed that they consistently existed. So these are ideals on a cardinal kappa, such that if you take the power set of kappa mod I, the quotient, it has a dense closed set. So this is a dense set that's closed under descending sequences. So descendingly omega closed, descendingly omega 1 closed. In other words, forcing with I is strongly distributive. So in particular, these are examples of precipitous ideals if it's less than omega 1 closed. We're also going to be using fine structure, in particular for L of E models. There'll be some innovative fine structure. Okay. Now, the forcing is going to be things that originated in the late 90s, early 2000s, so creating non-reflecting stationary sets, and then killing them while preserving other stationary sets. So if you create a generic non-reflecting stationary set, you can split it and kill one half and keep the other half still stationary. That uses the genericity of the set. So these allow coding arguments. So these appeared in papers with Cummings and Megador. We'll be using a version of Laver forcing. It's come to be called lottery-style forcing. So this allows you, in particular below a supercompact, it's lottery-style. So this allows you to generically choose the objects that you force with as you're doing an iteration. And finally, we'll be using coding in a serious way. Okay, so get out your dancing shoes and grab a copy of Kanamori Megador's exposition of large cardinals, the very classical one that talks about early large cardinal theory. So back in the 60s, even before the Beatles, Hennenfent and Kiesler and Tarski and others were interested in generalizing the first order properties to stronger cardinals. In particular, they were worried about compactness properties of L kappa kappa and other strong logics. So the large cardinals that came out were omega, of course, for first order logic, where you have real compactness. Weakly compact cardinals, strongly compact cardinals, and then strongly compact cardinals have some inconvenient properties. The lack of normality prevents certain kinds of nice things from happening. So super compact cardinals were developed and grew out of those. No, so Kiesler and Tarski is weakly compact. So the strongly compact came a little bit later, but the weakly compact came with Solovay-Reinhardt. Sorry, the strongly supercompact came with Solovay-Reinhardt Kanamori's papers, or Reinhardt-Solovay, Kanamori-Reinhardt-Solovay paper, which came. So no, this doesn't all, but what I'm going to be talking about is in the neighborhood of weakly compact and measurable cardinals, which came in the early 60s. In particular, it relates to a theorem from 1962-63, or published in 62-63, so probably earlier. So the first 3 of these correspond to compactness properties of languages. So weakly compact cardinals, I'm going to assume that you know the official definition, but Kiesler and Tarski proved the following characterization of weakly compact cardinals. Let kappa be an inaccessible cardinal, then kappa is weakly compact if and only if whenever you take a kappa complete subalgebra of the power set of kappa and a kappa complete filter over B, then you can extend it to a kappa complete ultrafilter on B. So at least for kappa complete subalgebras, you can take a filter and extend it to an ultrafilter. Of course, that's what you do when you prove the compactness theorem for first-order logic, so this is a very natural thing to do. Okay, so what is this talk really about? Hawley and Schlicht, investigating hierarchies of Ramsey cardinals, considered a collection of games. And these games were elaborated on in a paper of Welch and Nielsen. There's always suspense when I push the button. I move the mouse, okay, and then I click on it. Okay, I did click, I have been clicking. So. Anyway, I'm going to call the versions that we use in this paper Welch games, because I learned about them from Philip Welch. So here are the games. You fix a regular cardinal kappa and an ordinal. And okay. And an ordinal gamma, and players 1 and 2 alternate moves. So as usual, player 2 is the good guy, and player 1 plays kappa algebras. So each AI is a kappa-complete subalgebra of power set of kappa. The cardinality of AI is kappa. I'm just going to call those kappa algebras. And UI, so player 2 plays UI, which is a kappa-complete non-principal ultrafilter on AI. And the requirement is that these cohere. So if AI is a subset of AJ, so AI has to be a subset of AJ, and player 2 has to play an increasing sequence of ultrafilters over the AI. So the A algebras increase and the ultrafilters increase. So the game continues until either player 2 can't play, or the play has length gamma. So you keep playing. If player 2 can't extend the ultrafilters that she's played so far, then she loses. Otherwise, she wins if the game goes of length gamma. Okay, so at least is the game clear? So player 2 wins if the game continues all the way to gamma. Okay, so a couple of just comments. The first is that if kappa is weakly compact, then the Kiesler-Tarski result says that player 2 has a winning strategy in the game of length omega. Because all player 2 has to do to win is I already have, A3 and U3, and then you play A4, and then all I have to do is extend U3 to an ultrafilter on A4, and that's exactly what Kiesler-Tarski says that you can do. So if kappa is weakly compact, then player 2 can win the game of length omega. And if kappa is measurable, well, if I want to win, what do? I take the measure on kappa and I just put it in my back pocket. And no matter what algebra you play, I just play the restriction of my measure on that algebra. And I keep going. Okay? So there are two sort of trivial cases here. One is that kappa is weakly compact, and the other is that kappa is measurable. And the question that this paper is interested in is what happens in between. Now, let me give away the ending. This is about weakly compacts, but it should have generalizations to strongly compact, supercompact, and so forth, extender algebras, and so on. And that's completely open. We don't know anything about how to do that. We don't even know exactly what game is appropriate. So Nielsen and Welch showed that if player 2 has a winning strategy in the game of length omega plus 1, then there's an inner model with a measurable cardinal. So this is suggesting that there's a strict, the two cases are the only cases, the two trivial cases are the only cases, but this is an inner model with a measurable cardinal, not a measurable cardinal. So Welch's question is, if player 2 wins the game of length omega 1, is there a precipitous ideal? Okay. So can you get a precipitous ideal? Can you say something stronger about kappa than kappa is weakly compact? Now, thank you. Excellent question. I'll be answering a question of Velichkovich later in the talk. So we'll denote the Welch game G upper W lower gamma. All right, now, here's another thing. Suppose player 2 wins the game of length omega 1. And you collapse 2 to the kappa to have cardinality omega 1 with countably closed forcing. So you do the omega 1, 2 to the kappa collapse. Well, then player 1 can feed player 2's strategy from V. In V, player 2 has a winning strategy. So after you do that collapse, that strategy stays a winning strategy, because that just involves omega sequences. And you just start playing that strategy. And what you get is a countably complete ultrafilter on the power set of kappa. Okay, now none of us can resist taking the ultrapower by a countably complete filter. So you take the ultrapower by the countably complete filter, and you get an elementary embedding from V into M. Now, what have you done? You've forced with closed forcing that doesn't add new sequences, and you get a well-founded ultrapower. We're done. Precipitous ideal. Okay, except you forced with it. So the upshot is you forced to get an ultrafilter that has a well-founded ultrapower without adding any infinite sequences to V. You're done. Okay, except there's a problem. The ultrafilter you get is not generic. Oh, so what's the ideal there? The ideal there are those sets X contained in kappa such that you can't force kappa to be in J of I. So it's the usual ideal. Now the problem is that the ultrafilter you get is not generic for the power set of kappa mod I. And the definition of a precipitous ideal is you force with the power set of kappa mod I, and the ultrapower by that ultrafilter is well founded. So this proof at least is incomplete, and in the early 1980s, Laver gave a counterexample to exactly this kind of construction. So that proof doesn't work. So a little more work. Okay. Now, our main result is that if kappa is inaccessible and 2 to the kappa is kappa plus, then if player 2 wins the game of length omega plus 1, then there is a normal kappa complete precipitous ideal on kappa. Okay? So if you can even go of length omega plus 1, in fact, if you go omega plus a half, I'm not going to say what that means, but just a little bit beyond the Kiesler-Tarski, then there in fact is a precipitous ideal. So the Nielsen-Welch result got an inner model with a measurable cardinal, but this is a stronger result because we get a precipitous ideal, which then gives an inner model with a measurable cardinal. Now, where do the Laver ideals come from? So the stronger result is that if there are no kappa plus saturated ideals on kappa, strange hypothesis, but okay. If there's a kappa plus saturated ideal on kappa, then somehow the game's been, the mathematics has been washed out because kappa plus saturated ideals are very strong. So if there's no kappa plus saturated ideal on kappa, and you choose a gamma which is regular between omega 1 and kappa, and you suppose that player 2 wins the game of length gamma, then there's a normal kappa complete ideal I such that the power set of kappa mod I has a dense tree that's closed under descending gamma sequences. Okay? So this is a much stronger property than being precipitous. In fact, if you take gamma to be omega 1, then forcing with your ideal adds no omega sequences. The forcing has a dense omega closed set. Or you take gamma equal kappa, you add no less than kappa sequence, and you get an ultrapower. Okay? So this is getting very structured ideals from player 2 winning. And so this gets Laver ideals. There's a famous result of Rich Laver that gets a Laver ideal on omega 2. All right. So these are Laver ideals. The second kind are called Laver ideals. We need more wise guys in the audience. Is this vacuous? Maybe it's true that if you win the game of length omega plus 1, then kappa is measurable. So I still haven't answered the question, are the only two cases whether kappa is weakly compact or whether kappa is measurable, because all I've said is if you win these games, then you get these better and better ideals. If kappa is measurable, then you get an ideal on kappa, such the power of set of kappa modulo the ideal has exactly 2 elements, 0 and 1. And that's clearly closed under descending sequence. Okay, so, all right. So here's a definition. Let I be a kappa-complete ideal on the power set of kappa, and gamma bigger than omega be a regular cardinal. Then I is a gamma densely treed ideal if there's a dense set D contained in the positive sets such that it's a downward growing tree. D is closed under decreasing sequences of length less than gamma, and D is dense in the power set of kappa mod I. Now you can have, I mean, we all know this, you can have partial orderings which are closed under descending omega sequences that don't have dense trees. So it's a non-trivial condition that you have a dense tree. So you have a dense tree, and that tree is closed under decreasing less than gamma sequences. Okay, so the first theorem says that winning the game of length gamma gives gamma densely treed ideal. Okay, now here's the best answer I know to give to Boban's question. So so what we have is the games give ideals. How do we get from ideals back to games? How do you make this connection between the ideals and the games? So the theorem says that if you take gamma less than or equal to kappa, an uncountable regular cardinal, and J a uniform kappa complete ideal over kappa, such that the power set of kappa mod J is kappa plus infinity distributive, and assume that the power set of kappa mod J has a dense gamma closed set. So this is the hypothesis, this is the main hypothesis here. Then player 2 has a winning strategy in the game, in the Welch game of length gamma. So this is saying that if you have a nice ideal, then you win the Welch game. The Welch game says, the other theorem says if you have a good strategy, then you win, then there's a nice ideal. Now these ideals turn out to be incompatible, but that's a problem. You don't, if you start with the ideal and get the strategy and then go back to the ideal, you don't get back the same ideal, unfortunately, but let's ignore that. Okay, let me give a proof sketch. Since this was such a good question, let me try to satisfy Boban and give a sketch of the proof. Take D to be the dense closed subset, and let U dot be a term for the generic ultrafilter on the power set of kappa mod I. So this is the filter such that you're in the ideal if the possibility of kappa being in J of X is, has Boolean value 0, if that's impossible. So what is player 2's strategy? Player 2 builds a decreasing, player 1 is playing these algebras, A alpha. Now each A alpha has cardinality kappa. So player 2 builds a decreasing sequence of elements D alpha in the dense set. At stage alpha, player 1 presents player 2 with an A alpha contained in the power set of kappa. And by distributivity, there's a D alpha plus 1 below D alpha, which gives the intersection of the generic ultrafilter with A alpha. A alpha only has cardinality kappa. So by distributivity, you can extend to get an element of this dense set, which exactly decides A alpha intersect kappa. Now, player 2 can keep going because she's playing into this dense set. And because you're forcing something about the ultrafilter in the extension, these have to be coherent because you're all referring to the same object. So by the closure, this strategy continues of length gamma. Okay, so maybe that was too quick, but that's essentially the proof of this. Okay, so we reduced the problem of getting these strategies and separating these strategies to a question about getting ideals with nice properties. Okay, again, is it all or nothing? So if you win the game for some uncountable gamma, do you win the game of length kappa, for example? So here's the theorem, and then we have refinements, which I'll talk about. Assume kappa is measurable and that you're in some fine structural models. So you're in L of E. I'll give a special case outline if it's L mu, but Martin's done considerable innovative fine structural work to extend these to general L of E's. So, but assume L of E is a fine structural model. Then there's a generic extension in which kappa is inaccessible, carries no saturated ideals, so in particular is not measurable. And for all regular gamma between omega and kappa, there's a uniform normal gamma densely treed I gamma that's kappa plus infinity distributed. The ideal I gamma is not gamma plus densely treed. Okay, so what have we done? We have a criterion which tells us if you have a nice ideal, then you have a winning strategy. So this is saying two things. One is you can build a model over a fine structural model. I'll explain why that's relevant in a minute. You can build a model where you have these nice ideals. And moreover, if gamma is different than gamma prime, then these nice ideals are different. Okay, these nice ideals are incompatible with each other. So we've separated on the ideal level. So the upshot, again, is if you start with a fine structured L of E model, you can force to get a collection of ideals I gamma that construct winning strategies S gamma for player 2 in the Welch game of length gamma. And if gamma is different than gamma prime, then the Welch strategies are incompatible. Now, I haven't quite done what I promised, namely, if you ask me gamma omega 2, I mean, first of all, if I can win the game of length omega 2, I can clearly win the game of length omega 1. Why? Player 1 starts playing, I just play my strategy in the game of length omega 2. And if one quits at stage omega 1, that's not my problem. Okay? He just lost. So if you have a strategy in a long game, you have a strategy in the short game. The question is, does a strategy in the game of length gamma extend to a strategy in length gamma plus? And in this case, it doesn't. And moreover, I don't know if this, do I have a slide on this? Yes, more precise information. You can do this and only have it for a maximum gamma. So if kappa is a measurable cardinal and gamma less than kappa is a regular uncountable cardinal, and V equals L of E is a fine structural model, then there's a generic extension in which kappa is inaccessible, carries no saturated ideals, so is not measurable, and there's a uniform normal gamma densely treed on kappa, which is kappa plus infinity distributive. So you get the strategy, but it's not gamma plus densely treed. And in the generic extension, there's no uniform ideal I prime over kappa, such as the power set of kappa mod I prime has a gamma prime closed subset when gamma prime is bigger than gamma. 2 does not have a winning strategy in the Welch game of length gamma prime whenever gamma prime is bigger than gamma. Okay, I'm talking really fast, saying a whole bunch of technical things. What's the upshot? The upshot is you can separate these Welch games by forcing over a fine structural model. And again, if you win a long game, you win the short game. But if you hand me a gamma, we can play up to, I can create a model where player 2 wins the game of length gamma, but doesn't win any game of any longer length. Okay, so this is what's going on. Okay. How does the fine structure creep in? I mean, usually these forcings, okay. I confess I'm used to saying, let kappa be supercompact, and now we'll iterate the following things. And the issue whether there's an inner model for a supercompact doesn't come up. So this is a quite interesting thing. So the simplest case of the construction, L of E model, I think of L mu, which I know is wrong. I'm completely wrong, but I'm an amateur. The simplest case is for L mu. So in the core model, you have a canonical definable sequence of square sequences, so I'll call square infinity. So for each regular alpha, you have a square alpha, or let's take alphas to be inaccessible. And it's so canonical that if you take the elementary embedding from the measurable cardinal kappa, from L mu to M, and then square kappa, so in the ground model, you have this long sequence of square sequences. You look at the square sequence at kappa, then these are uniformly defined so that if you take J of the sequence and look at the square sequence at kappa in M, these are the same square sequence. Okay, this is the core model square sequence. So this allows the definition of canonical sequences of non-reflecting stationary sets that you can use for coding purposes. So what's going on then is you do a coding in V, and in V, you know exactly what forcing you're going to do at stage kappa in this generic extension, in this generic elementary embedding. usually a problem is you do an iteration up to kappa, not including kappa, and you take j of the iteration, then what you're doing at kappa depends on the generic object up to kappa. But this canonical square sequence means that already in V, you know on the M side what you're going to do at kappa. Okay, so the theorems are proved by iterating up to kappa with Easton support. You use a lottery to choose the gamma alphas at inaccessible alphas less than kappa along the way. In other words, you're going along, you get to alpha, you flip a coin, you roll a dice, and you choose gamma. That's a condition, so the condition decides what gamma you have. Then you add generic non-reflecting stationary subsets of kappa plus, and you kill other stationary subsets of alpha plus, and you kill other stationary subsets of alpha plus, and these interact with the non-reflecting stationary sets coding gamma alpha, and therefore in V at stage, in V at stage kappa, if you tell me what gamma kappa is, even though you've done all these, you've added lots of subsets of kappa up to there, I know exactly what the forcing is at stage kappa. All right, so how do you get the relevant ideal? We forced up to kappa with P for the intended gamma. So the bad guy gives you a gamma at kappa, and I have to build an ideal. So for the intended gamma, you consider the condition in J of P that chooses gamma. Because everything is canonical, fine structure, the forcing over M is the same as doing the corresponding forcing in V. So the forcing is determined by the canonical square sequence. And then the ideal is the usual ideal. So I gamma is the set of subsets of kappa such that it's impossible that kappa is in J of X. So the Boolean value that kappa is in J of X is 0. In the forcing below the choice of gamma. And then the general duality phenomenon, which is that the power set of kappa modulo the ideal is isomorphic to the forcing you need to create the ideal, says that the power set of kappa mod I gamma is isomorphic to the Boolean algebra determined by the forcing. But the Boolean algebra determined by the forcing, if you have a non-reflecting stationary set of cofinality gamma ordinals and you shoot a club through it, that forcing is less than gamma closed. I mean, you can't get in trouble if this set is a subset of cofinality gamma. You just start building, it's gamma closed. So, okay, so the forcing is gamma closed. The power set of kappa modulo the ideal is isomorphic to the forcing. So now you take the inverse image of the dense set consisting of the forcing. Shooting club sets gives you a tree. It's a tree that's gamma closed, and you're done. Okay, so now there are additional difficulties if you want to just have one gamma. Remember, the theorem is that if you hand me gamma, we can create a model that, or hand us gamma, you can create a model such that gamma is the largest cardinal where you have a strategy of length gamma. This creates additional difficulties if you only have one gamma because of issues around ghost coordinates. And this is the main reason that new fine structural techniques are involved. So the second reason new fine structural techniques are involved is that we're working over arbitrary L of E models, not just L mu. So these results appear in part 2 of the paper. Part 1 is on archive. We have a better version that's about to be submitted. So we'll put the new version on archive when we submit it, or send me an email. So these innovations are aimed at interactions with Easton supports, but because they're sufficiently strong that they seem to apply to a much broader collection of interactions, non-stationary supports were mentioned, this kind of thing, they apply. Okay, let's go back to playing games. I have 20 minutes left. What's up with the inaccessibles? I mean, it's a little amusing with modern eyes to try to go back and look at the Kiesler-Tarski papers and the Kanamori book. I mean, Aki's written a lot about these things. They don't ever really explain why the hypothesis is inaccessibility. They're generalizing properties of omega, and omega is inaccessible, so you have inaccessibility. What happens if we play the Welch game at a non-inaccessible cardinal? I like it when omega 1 or omega 2 are generic large cardinals, so let's bring this down to earth. Unfortunately, these turn out to be necessary. I'll talk about this in the open problems part. So the next results are really a throwback to 1960s style, very naive and easy mathematics, but I don't think it's been done. Okay, so the proposition is take your favorite infinite cardinal and assume that kappa is either a strong limit cardinal or that there's some gamma less than kappa, 2 to the gamma is bigger than kappa, but for every gamma prime less than gamma, 2 to the gamma prime is less than kappa. Okay, this is weird. There's no Boolean algebra contained in the power set of kappa, which is both kappa complete and has cardinality kappa. So once you say it's kappa complete, well, you can use the kappa completeness to generate too many sets, so the cardinality of A is bigger than kappa. Okay, and I have to mention James was very helpful in talking about these kinds of things, so I want to acknowledge James Cumming talking about this with me. Okay, the second proposition is take kappa infinite and 2 to the gamma kappa, 2 to the gamma equals kappa. Well, it's a triviality that the power set of gamma is contained in the power set of kappa, and the power set of gamma is a complete Boolean algebra, so in particular it's kappa complete. Okay, now, what happens if we're back playing the game on kappa, the Welch game on kappa, and player 1 plays the power set of gamma? Okay, well, I'm trying to respond to this, but I can't play a non-principal kappa complete ultrafilter on the power set of gamma because kappa is bigger than gamma. Okay, so what's the upshot here? This is the theorem. If kappa is an inaccessible infinite cardinal, then either you don't have any subsets of the power set of kappa, which are kappa complete and cardinality kappa, in which case player 1 can't play, or there's a kappa complete subalgebra of the power set of kappa that has cardinality kappa, but every kappa complete ultrafilter U on A is a principal ultrafilter. So what are the two cases? Either player 1 can't play, or player 2 has a play that player 1 can't respond to. So this game is either dead at length 0 or dead at length 1. Player 2 can't even win the game of length 1. So this looks very bad for what's going on at non-inaccessible cardinals. Yeah. Okay, but you decide them in a kappa complete way. Then that's equivalent to deciding it on the kappa complete algebra. I would love to know the answer for p kappa lambda. Okay, so that's another open problem that's coming. Okay. Okay. So where do the ideals come from? They can't come directly from the elementary embedding. Why is that? The elementary embedding, remember the ideals here. So we have two ideals. We have the ideals that are coming from the strategies, and we have the ideals that build the strategies that come from the elementary embeddings. Now, the ideals that build the strategies have to be kappa plus infinity distributed. You can't add new subsets of kappa. The ideals that are built from the strategies have dense trees of height gamma less than kappa. So in particular, if you know the generic object on this set of size gamma, namely the branch that it concentrates on, then you know the whole forcing. So the strategies built by the ideals built by the strategies are not kappa plus infinity distributive, but the ideals you need to build the strategies have to be. So the relationship between the two ideals is not completely clear. So the ideals have to come somehow by the filters being played by player 2. Okay, now we get to politics. You can't keep politics out of anything anymore. These are hopeless ideals. Now, let S be a winning strategy for player 2 in the Welch game of length gamma, and you take a position P. Suppose you're a subset of kappa, and you haven't been in any of the ultrafilters, and your complement hasn't been in any of the ultrafilters, and you still think of being in the ultrafilters making it to the 1%, the wealthiest 1% of your country. Okay? And so far, you're still, in the middle somewhere. You're hopeless. When can't you make the 1%? It means that there's no extension of the position where you've played so far where you end up in the ultrafilter. Okay? So it's hopeless for you in an extension of, you have a history, and it's hopeless for you to get into the 1% given your history. Okay? So this is the conditionally hopeless ideal conditioned on P, where P is this partial play. This is the play so far. Okay? All right. Now, the unconditional hopeless ideal, so some of us are born hopeless. So the unconditionally hopeless ideal is the hopeless ideal conditioned on the empty set. So with no history whatsoever of the game, you still can't make it into any ultrafilter. Now, why are we interested in hopeless ideals? Well, hopeless ideals are kappa complete. This is easy to verify. You're playing into kappa complete filters. So if you never make it into a kappa complete filter, well, if you have a collection of alpha sets where alpha is less than kappa, then their union can't make it into any filter because that filter would then have to choose one of those sets. Okay? So the hopeless ideals are kappa complete filters. And so maybe that's a place to look. I mean, we have to come up with ideals somewhere just from the strategy. So this is a place to look. All right, so here's I mean, the proof is 30 pages long, so I'm not gonna do it. Start with the strategy S in the Welch game, and you build another strategy, S star, in a slightly different game, such that S star plays sets xi, and the xi's diagonalize normalized ideals on AI. Now, AI is cardinality kappa, so normal doesn't quite make sense, so you have to know what internally normal means. This involves internally approachable sequences of structures, et cetera, et cetera, et cetera. So there's technology here, but S star plays sets that diagonalize normal ideals on AI. When you do this correctly, all of the conditionally hopeless ideals for S star are equal to the unconditionally hopeless ideals. So no matter what you do during your lifetime and you're at player P, if there was hope for you when you were born, there's still hope for you. Okay? So the hopeless ideals are the same, the unconditionally hopeless ideals are the same as all of the conditionally hopeless ideals. And moreover, these plays can be organized into a tree. So with these properties, the unconditionally hopeless ideal has a dense gamma closed tree, namely the collection of sets played by player 2 in S star. If you're playing a game, then the results of that game form a tree, depending on how you respond. And so you get a dense tree, namely these sets played by the strategy S star. Okay, again, we build a sequence of auxiliary games. G0 is the Welch game. We have G1 minus, G1, G2, and a sequence of strategies starting with S gamma. And the later strategies simulate the earlier games. So these games become simulated games for the earlier games, auxiliary games for the earlier games. Now let me get to Mirna's question. One particularly tricky transition is to require player 2 to play normal ideals. Now why is this tricky? It looks simple. If you have, say, an elementary substructure of H theta and you have a kappa complete ultrafilter on the power set of kappa for that structure, then you can normalize that ideal by taking the ultrapower of that structure by the kappa complete filter and then take the filter concentrating on kappa. And the result is a normal ideal on that elementary substructure of H kappa. So if Matteo plays U, and I'm playing the game where I have to play a normal ideal, I just take his play and I normalize it and I play the normal version. The problem is he may be playing a decreasing sequence of ultrafilters, but it's not true that if you have U a subset of V, then the normalized version of U is a subset of the normalized version of V. Okay, so homework over lunch, give an example of that. So this looks like it's very hard to transform this game from ordinary ideals to normal ideals. But the trick is that the cases where you don't have this subset form a well-founded tree. And so if you start by, again, you simulate, you have to build a new strategy, but you start by saying, okay, let's go beyond this ill-founded tree. And we start by playing ultrafilters that are beyond one of the roots of this ill-founded tree. So that's how you get around that problem. But let's go back to this. We need this technology to take an ultrafilter on kappa and transform it to a normal ultrafilter on kappa. Mirna asked me about p kappa lambda. Okay, we all know this whole history with lots of wonderful results that you can't transform an ultrafilter, you can't transform a fine kappa complete ultrafilter on p kappa lambda to a normal. There's to a normal fine kappa complete ultrafilter on p kappa lambda. You can't go from not every strongly compact cardinal is a super compact cardinal. So immediately the generalization of this to p kappa lambda starts looking, okay, something else is going on. Okay, now working on these games was really fun. It's fun to, listen to 60s music. Lots of challenges came up. But we have all these tools, how many, 60 years later? And the tools are really wonderful because you think about it a little bit and then you just grab the right tool and the tool is on the shelf. So these are very, very, very nice things to work on. So this is the modern remix of results of Kiesler and Tarski. What are the remaining open problems? Are they as tractable as the question of weakly compact versus measurable cardinals? So are they as tractable as what we did? All right, the bottom line is really the right thing here. What are the open problems? Ask me a question after the talk or here, and the answer is probably, I don't know. This is really not well-trodden territory, but it is very encouraging to me that, again, things come up and you just take them off the shelf and you use them. So the first one is Mirna's question: are there analogous results for strongly compact cardinals? And my response is, I don't know, I don't have a clue, I can't even conjecture what the result would be, because you can't normalize strongly compact ultrafilters to be super compact ultrafilters. So one of the basic steps in this proof has to change. Another question is, what's the analog for successor cardinals? We showed that this game doesn't make sense except for inaccessible cardinals, but there should be some way of changing the game so it does make sense. Okay, so just like if you collapse a measurable to be omega 1, you get a precipitous ideal. There should be some version of this game at omega 1 that miniaturizes what this game is, but not a clue. What about extenders? So Ralph and I talked about this a little bit. There seems to be reasonable ways of trying to change this into an extender game. So you're staying in the LV context and you're staying in the situation where you can normalize filters. I think to me, that looks very promising, where you change the game to playing extenders. What happens in the games if you play ideals themselves? So this is close to the Holly-Schlick games. If you start being required to play ideals on various ends, does that somehow help you get to the case where you're at a successor cardinal? And nobody asked me this: what's up with the saturated ideal or the continuum hypothesis? We have two very non-trivial hypotheses here, even in where we were proved things. Namely, we required that 2 to the kappa is kappa plus. What happens without that GCH requirement? And the saturated ideal looks like a total non sequitur there. Okay, so especially if you're starting in something like L mu. Now, again, I don't promise I can't answer your question, but I am promising you this is really untrodden territory. Thank you very much. So I should go to...
Thanks, Matteo. Thank you, Mark, for this fantastic talk. I just want to clarify a little something about this p kappa lambda, which might
Okay.
So I was thinking of cardinals which are called nearly lambda strongly compact.
Nearly lambda strongly
So
compact.
these are cardinals that are actually between weakly compact and measurable cardinals.
Okay.
And well, we came to study them in some questions in compactness, something called square compactness in topology.
Okay. Pull your mask down just for a second.
Oh, yes, sorry. So this comes from my work with David Buhagiar on the question of when you take a less than kappa compact space, topological space, and you want that a square of such a thing is always less than kappa compact. This is called square compact, was defined in Juhas's thesis a long time ago. Okay. And the exact large cardinal strength of this was known to be between weakly compact and strongly compact, but nothing more. And we put it below measurable using this notion. Okay. And the notion comes from a thesis of White. Every family A of lambda many subsets of P kappa lambda can be measured by a non-principal less than kappa complete fine filter F over P kappa lambda. So you actually have this extra parameter of not working with ultrafilters, but working with some family of a bounded size. And then you can show that this is equivalent to an extension property of filters, which is, we call it lambda filter extension. It says that whenever you take a family of size less than or equal to lambda of sets in P of 2 to the lambda, so you take a family of subsets of 2 to the lambda, and this family has size less than lambda, then every less than kappa complete filter generated by its most lambda many elements can be extended to measure this family you have. So this is kind of localized ultrafilters with this parameter, and it seems that it might have something to, well, that you might say something relevant with these Welch games, and in particular, perhaps you could answer what is left of this question, which is very old, from 1975, which is to find the exact consistency strength of square compact.
I see. Okay. Yeah, no, very nice question. And I mean, what that last condition you gave is analogous to this Kiesler-Tarski condition. Yes. I am hoping to get this above, into the vicinity of questions about strongly compact, which, I mean.
Yeah, this is called merely strongly compact because it's a mini version of strongly compact. Yes, a mini version,
yeah, exactly. So, but very nice. Okay, so here, there's a theorem on the shelf here from somebody who has the energy to go get it.
Are there other questions from the audience here?
What kind of extender game were you thinking of?
Oh, something like this. You have and now I'm going to show my lack of knowledge, but you have an extender with some support. And player one starts playing, subalgebras stating what the support is and what the subalgebra is, and then lunch is calling. Player two has to respond by an ultrafilter on that set, on that extender set, and maybe you get a J from V into M with P squared kappa contained in M. This has the advantage, again, that you're really morally only working with ultrafilters on kappa at each stage. I mean, it's the same reason extenders are nice for intermodel theory. You don't get stuck in this P kappa lambda swamp. But I don't know any answers to this. And I have to say, this was Ralph and I have discussed this.
Other questions? Okay, here in the audience, I don't see any.
Wait, Philip is asking.
Yeah. So, I think you've asked this as well, but can you say anything about the relationship between Ulam games and these games here?
Okay, remind the audience what Ulam games are.
So I mean, you've got, player one is making two choices, and then player two is just taking one choice, picking one out of these two sets. And you continue in this way, and you want to see whether there is empty intersection at the end or not.
So this is a form of a cut and choose game.
Yes.
So the answer is no, I don't know the relationship.
I mean, whether
if
one
okay,
says
well,
something
so
about
let
somebody
me-
having a
let me
strategy
go
in this
back.
game, it doesn't mean they have a strategy in the other. Okay.
Well, so if you win the Welch game and you start playing the cut and choose, the cut and choose options to me, I just put those into some kappa algebra, and my ultrafilter. I mean, if you're giving me complementary sets, if you're really cutting each time, then one of those two sets has to be in the ultrafilter.
Yes.
And then once that set's in the ultrafilter, when you split it, one of the two things has to again be in the ultrafilter. So winning the Welch game gives the asymmetrical cut and choose game gives the good guy, the person who has to have the large intersection, a winning strategy. But that's a trivial comment. I mean, for example, the cut and choose game where both players split, I have no idea. And the ideal game of Galvin, Yek, and Megador, I think, player two winning the Welch game is much stronger than winning that game, even playing the long versions of that game. So.
Fine, thanks.
Sure.
Are there other questions from the web?
Yeah, can I ask a question, Matt? What about the first inaccessible? Can you get there?
Say again, what about?
The first inaccessible.
No, because even winning the game of length omega implies that kappa is weakly compact.
Oh. And another thing.
Oh, wait, I'm telling the truth? Okay, I'm telling the truth, okay.
Yeah, I see. Another thing, can't you replace the fine structures by just forcing some kind of canonical velodering of V and then using it to choose stationary sets?
So when you're at stage alpha, you're forcing a subset of alpha plus. So
yeah.
When you force up to kappa and stop at kappa, on the M side, you'd be building a well-ordering of length kappa plus, and that's not going to live in V when you've already forced up to kappa. On the other hand, if you do just that forcing to recover what you have over M, then when you take J of that, you need master conditions, and that adds complications. So
yeah, that's what I mean, basically, to some way produce canonically master conditions,
yes.
then just use this sequence.
So I don't know, that's not, we didn't succeed doing it that way. That's.
Thank you.
I mean, yeah. Menachem and Martin know fine structure very well, so it was easy. This was the route that was easier. But I don't know the answer whether that worked.
Thanks.
Other questions? Okay, it seems we are happy with the questions so far. And so we can thank Matt again.
Thank you.